talk about artificial selection. The only difference between artificial selection and natural selection is the selecting agent. Natural selection literally means what? Who selects? Nature selects the most fit variant. Artificial selection, who selects? We do. We decide what's most fit. So we do this all the time when we basically create agricultural products and domestication of animals. So here's a nice example. This is the mustard plant. If you've ever been anywhere in Ivy or anywhere, when you guys travel south and you go to LA at certain times, have you ever seen the mountainsides and they're covered in all that yellow flour? That's mustard, okay? So mustard is an invasive plant. It doesn't belong here, but it was brought over by the Europeans, and it's a weedy plant. It's R-selected. It spreads all over the place. Any disturbed habitat, it grows very well. It's also quite edible. So we modify it for all kinds of things. So obviously it's mustard, so the seeds are ground up for what? Mustard spice and mustard, the paste that you put on your stuff to eat, right? It's really tasty, it's quite delicious. But the whole plant is actually edible. It has kind of a bitter taste to it. In its natural form, it's very consumable. You can eat mustard, no problem, right? And so this is what it looks like as a wild type. This is how it naturally occurs. In the population of mustard, if you were to stroll around in a patch of it, next time you see it growing in a place, a garden, or in a park or something, or out in the field, go just walk around in it a little bit and look at it. First thing you'll notice is there's some plants that are tall, some that are short, some that are broad, some that are skinny. There'll be ones that are real dark green and light green and purple, and there'll be some with flowers really big and flowers really small. They display variation in the population just like we do, okay? We utilize that variation for particular purposes, and we cultivate certain crops from this particular plant. And so I'm going to kind of run through some of the things that we use. So the scientific name of the organism is Brassica oleracea. And so we select for the leaves. So the first thing I notice when I walk into a wild population of mustard is the leaves can be really big and broad and flat. Some can be crinkly, some can be real thin. And so what we do is we say, okay, those leaves are really tasty. I wish I could make them bigger. Well, how do I do that? I just grab the wild type plant that has a big leaf over here, and another one with a big leaf, and then I propagate them, I pollinate them, and then I grow them, and then I do the same thing again and again and again and again and again. And lo and behold, you do that over and over again, and this thing's been cultivated for about 5,000 years, right? So if that's the case, you think how much you could do over that time span, right? You could create a leaf this big. Has anyone ever eaten mustard green before? Anybody from the South? Mustard greens are really good. They're basically a cuisine from the south parts of America. They're quite tasty. They're a little bit bitter. You should have them and try them out. How about kale? You've eaten kale? Raise your hands if you've eaten kale. You're Californians. You've eaten kale. They throw it at you no matter where you go. So some people love kale. Some people don't quite like it. But kale comes in 100 different varieties, right? There's purple kale and green kale and curly kale and smooth kale. It's all mustard. All that's been modified is by taking leaves of certain shapes and certain colors and breeding them together over and over and over again to isolate that character and develop it through time. But it's just mustard. It's the same plant. All right. That's modification of the leaves. There's also modifications of the stem. So when you take a look at mustard, some mustard is real thin, others is real thick. By breeding mustard plants together that have thicker stems, you can create this product. That's kohlrabi or bok choy. How do you eat that? It's just mustard, okay? It's just a modification of the stem, selective breeding for that particular phenotypic character over and over and over again. This is selection for the flower. Broccoli is mustard. Cauliflower is mustard. Isn't that crazy? So everybody's eaten broccoli before, right? It's one of the favorite food vegetables in America, right? So broccoli is very tasty. All it is the flower bud before it opens up. How was it created? You just went out to wild mustard and you saw the ones that had big flower buds. You grabbed them, you bred them together over and over and over again. Lo and behold, before you know it, you get broccoli. How you can actually do this test for yourself. If you leave broccoli and don't eat it, and just let it sit in your refrigerator for a while, and just let it sit on the counter, the buds will open up, and what color are they? They're yellow inside. What are you seeing? You're seeing the flower from the mustard, okay? Cauliflower is one that's relatively apigmatic, so they basically modified it for not having as many of the chlorophyll, having a low chlorophyll content, and then they also cover it up typically with some screening to prevent the light from hitting it so it won't stimulate the photosynthetic pigments. But you can get cauliflower in all kinds of colors. You've seen it with colors. Purples, oranges, and yellows, all within the variation that you find within wild mustard. Okay? Here's an interesting one. You can also modify the bud where it first comes out of the ground. And these are called the terminal buds. So when the plant first comes out of the ground, it comes up straight and then it buds off on the sides like that. This is the terminal bud and these are the lateral buds. So when you modify the terminal bud, you create cabbage. So that's actually mustard. There's green cabbages and purple cabbages and a whole variety of different cabbages. Again, just modification of the basic mustard plant. And then there's this one, which is really neat. That is Brussels sprout. So remember I told you that the buds spread out and go sidewards? Those are modifications of the lateral buds. Okay? That's what, everybody seen a Brussels sprout plant in real life? They're actually quite bizarre looking. They almost look prehistoric. They're very strange. But this is what they look like when you peel back the leaves. Notice the leaves look like giant mustard greens. So all of this is the same plant. It's all mustard genetically. Now here's the really interesting thing about this. This has been so heavily modified, they can no longer breed with the parental plant unless we crossbreed them back. Some of them are so heavily modified, they can't even generate their own variant anymore. That's how heavily modified they are. The reproductive parts are also do that. We don't care about that because we're producing them ourselves, right? So, but this is artificial selection for certain phenotypic traits. Why does it have this? Because we selected it. Doesn't mean it's necessarily fit for the natural environment. It's just fit by our standards because that's what we want. A long time ago, I teach a smaller course that I used to teach for non-majors where I display this to them as well. And they're totally blown away by it because they've never seen anything like it. And it's funny, when I first started teaching it, I would grab the stuff as a live demo. And which is really cool. I would have done it to you guys, but you're a little more advanced than that. Sometimes people look at it as kind of lame. So I don't do it for you guys anymore. But I still do it for them. But it's not that lame. It's actually very cool. Because so you get to see the wild type plant, and then you get to see all these horticultural variants of it, you know? So they're neat because you toss them out. I like to have things be, for me, I understand something when I get to touch it and feel it and taste it, you know? So I like kind of that aspect of biology. But what's interesting about it, so I would toss all this stuff out, and the very first time I did the demo, right, I had to collect all this junk from the grocery store, and some of it's seasonal, so you can't get it all the time. And one of the things that are seasonal are Brussels sprouts, and I didn't realize that at the time. So I was looking for Brussels sprouts, and I couldn't find them. So I said, well, maybe they have them in the frozen section. So I went to the frozen section, I saw Brussels sprouts, and I just grabbed it, and I didn't think twice about it. And so I brought it into class, and it had kind of thawed out, and I realized, well, they're cooked Brussels sprouts. They weren't like raw. And I said, well, hell, I'll just use them anyway. It's not a big deal. So I throw all this stuff out, and I opened the box, and they were kind of gross because they had like thawed on the outside, but they were still like an ice ball on the inside. And it was a fairly long room like this, and I was throwing the stuff out, and then people like will raise their hands to catch it. And so I would like throw it, you know, like this. So I remember I had this Brussels sprout in my hand. And I was sitting there, and out of the corner of my eye, I thought I saw someone raise their hand. So I had the Brussels sprout, and it was like way in the back. I'm like, yeah. So I heaved it. Brussels sprouts go pretty far. And I threw it really hard to get it back there. And then, you know when you do something bad, but you can't take it back? And like time slows down? It's just like that. It's just like, no. I just couldn't grab it back, and it was flying through the air, and I realized the person was just scratching their head. And so I got a decent arm and rifled back there, and I remember it was all slow motion for me, and I'm watching it, and it hit this person dead in the face. What was terrible about it, since it was partially thawed, the thawed part exploded. And then the the ice ball part just detonated on the forehead. I was like, you see someone get shot and we were there all. And so I was like, oh, damn. So I ran back there, and there's this poor girl, and I hit her dead center. And I'm looking at it, and unfortunately I have a really sick sense of humor. And I'm looking at her, and she had this like bright red dot in the middle, and then a bright green ring. And I looked at it, and I'm like, are you okay? And all of a sudden it struck me as like the funniest thing ever. And I started to laugh uncontrollably. Like the biggest like butthead in the world, right? I'm laughing at this poor student that I've just assaulted with Brussels sprouts. And I was like a brand new professor at the time. I'm thinking, my first day I'm getting fired for assault with Brussels sprouts. Luckily she was very cool about it. That's why I don't do it typically anymore. And if I do it, never with a cooked Brussels sprout, always with the raw variety. So this is a really nice example of how you can select for traits. Another nice example is the domesticated dog. So we have done all kinds of terrible things to the dog. When you look at all dog genotypic characters are quite plastic morphologically. They're really easy to manipulate because of the way the genes are lined up. And so we can modify and do all kinds of things, which we did. We created these giant behemoths, these little tiny things that fit people's purses. Don't do that, that's terrible. And so, and all these different shapes and sizes of dogs, and we modified colors and on and on and on and on. And so this is another example of artificial selection. I always wanted to do this kind of demonstration, and that's like, first I would walk in with a like wild dog. Like either, you could do it, I do it like a wild African dog, which are beautiful animals. If I really wanted to do it from the domesticated dog, I could bring in like a wolf or something like that too, another kind of canine. But the African dog's so cool. So I'd walk that in, and you ever seen African dogs are these beautiful animals. They got the big tip on the tail, and they're just, these really amazing creatures. And then I would show it to you guys and prevent it from trying to attack you. And then I'd be like, yes, very cool. And then I'd walk out the door, and then I'd come back in, and I'd have like, what's a terrible dog? A pug. And I would hold it like this. And I'd look at it with the stain, and I would show it to you like this. And I'd be like, this is what we've done via artificial selection to this one proud animal. And at that point, I'd feed it to the wild dog. If you're a pug lover, I apologize. They don't even bark, they snort. What the hell is that? You're taking away the fourth bark. So that's artificial selection. All right, so we're moving forward in the microevolutionary process. So, variation acted upon by natural selection can lead to genetic divergence. And that's what we want to talk about today. So, when we think about genetic divergence, we're talking about dissimilarity in the genotypes between daughter and parental populations. So let's start with gene flow. So, gene flow is simply the movement of alleles into and out of populations. We actually examined this in ecology, but we weren't concerned with the genotypes. We were just concerned with individuals flowing in or out of subpopulations, right? Well, in this case, we're looking at exactly the same phenomenon, but I'm interested in the flow of the alleles in and out of the populations, right? So, if you basically emigrate with an E out of a population, you take all your alleles with you. If you immigrate into a population, you carry a whole new set of alleles into that population, and you're contributing to that population. So you either add or subtract alleles from a given population. Now, what does this do? Gene flow has a tendency to homogenize the genes between subpopulations while increasing the overall allelic composition. So what does that mean? If I have separate subpopulations, often they are quite distinctive genotypically. When I start moving alleles around, I make them more similar, right? But I've also added alleles to each of the subpopulations. So the overall amount of allelic combinations can go up, but so does the similarity between those populations, which basically gets rid of the differences. So it homogenizes the differences in the allelic composition among subpopulations. So what's an example of that? Take a look at jay. So jays are really smart birds, right? They're one of the few animals that does well with us because they're smart. They occupy our habitats. They can forage off our gardens and in our garbage and all kinds of stuff like that. And they're heavily generalist animals. In nature, you often find them in the forest, and one of their favorite things to eat are walnuts. And so what they will do is they take walnuts, they will grab them, and they will fly them back to their home range, and then they will bury them for the winter. So they will store them, right? So when they are plentiful, they will grab them from all over the forest and bring them back to one place and store them. And it's not just one little place. They have caches all over the place. And since they're animals, and when you put something in a safe place, what often happens? How many times have you done this? I'll put it in a safe place, and then you forget where the hell it is. It's no longer safe. It's now lost, right? Well, they do exactly the same thing. They forget where their caches are. So what they've done is they've collected an acorn from over there, or a walnut from over there, or an acorn from over there, and they moved it here, and they moved it over here, and they moved it over here, and they moved it over here. So what are they doing? They're basically taking from a little subpopulation over there and moving the allele over here, and taking it from here and moving the allele over there. So what they're doing is they're homogenizing the allelic composition of the entire population of walnut trees as a whole, right? However, that movement was critically important in doing so, okay? Because what was happening was this little grove of trees over here was in a real dry environment, and they were having a whole series of adaptations to deal with the water loss. Over here, this group of trees was sitting on a really rich little patch of soil over time, and they were basically having a series of physiological adaptations to deal with that soil content, or it was too acidic or whatever. Well, all of a sudden I grabbed an acorn from over here and I moved it over there, and over there to over here, and I've just homogenized the allelic differences between the two. So in a way, what gene flow is doing is reducing your ability to adapt to local environments. It's slowing the speed of evolutionary change. Does that make sense? So by homogenizing allelic composition, you're basically counteracting genetic divergence. Each of these little subhabitats, organisms are diverging in different ways to deal locally with those problems that the environment puts forward. Gene flow back and forth is basically slowing down that process of specialization. A nice example is the human species. So, based on fossil record, our most likely site of origin is in the central part of East Africa. From that site, we migrated across the entire world. We first came out into basically we came out of Africa, went into Europe. From Europe, we went across the European continent and Asia, and then we went down into South America, over the Bering Strait, down into South America to North America. So you can see all the kind of the lines of human migration across the planet. Now, here's the thing. We're talking about how many years ago? A long, long time, right? A long time. And so, was there an airplane back then? No. So how'd you get from Africa to Europe, and from Europe to Asia? You walked. And as you walk, you're talking multi-generational travel in some cases. Are the environment the same in sub-Saharan Africa as they are in Northern Europe? Is it the same as it is in Australia or South America? They're radically different environments. So as that migration went on, what phenotypically began to change? Hair color, eye color, height, all these things. That's why we have all of these racial differences, because they're local adaptations to different environments. Why is it that people whose ancestry is along the equator have dark skin? It's a sunblock. It's just natural melanin sunblock. Do you need it up at the top near the Arctic Circle? You don't need it. So that's why the skin is lighter. So you can see that's a low. So basically, if you're a real fair skin, and I stripped your butt naked and threw you down in the equator for a couple hours, what would you look like? You'd be bright red lobster, okay? If you have blue eyes, your eyes would get really messed up too. They get sunburned as well. The opposite is if you're real dark skinned and I threw you up in the Arctic Circle for a while, you see how palms actually metabolizing certain kinds of vitamins and things like that because you're not getting enough sun penetration to the skin because you're too well defended. So there's all these kinds of nuances. So all these kinds of little micro differences in our population as a human species are all due to local adaptations to environments. We're solving problems in different ways. That's all it is. What's interesting about that now is as a species, because what has increased among us now as a species? We don't have to walk anymore. What do? We drive or we fly anywhere. I can be anywhere in the world within 24 hours. What do I carry with me? I carry my genes with me. I carry my allelic composition with me. And can I share it? If I so desired, I can share it wherever I went. All right? And that's what happened. So what you're basically doing then is, what are you doing to these differences? You're homogenizing them. That's exactly right. So if basically we would have spread out like this and never developed mass transit of any kind, these differences would have continued to increase and remain very much separate. However, today, it's all being homogenized because of modern technology and flight. And all of these tendencies are being homogenized again. Why? Because gene flow is an operation in a heightened regard in terms of our societies around the planet. So it's another nice example of kind of the stretch into local adaptation and then reduction because of homogenization due to the flow of genes. The opposite of this is genetic drift. And this is typically the one thing that most people have a hard time understanding. I'm going to present it fairly simply here. Genetic drift is a chance thing. This is the part of evolution that most people don't recognize very well, and it's chance. So, it's the random change in allelic frequencies over the generations brought about by chance events. So, you're going to get changes in your allelic frequencies that occur regardless of your fitness, because chance will basically do it. I talked about the idea of the bus just hitting you, right? So genetic drift has a tendency to do two things. It either eliminates completely or it fixes completely an allele at either 0 or 100% of the population. It has a much larger impact on small populations than it does large populations. Large populations, in terms of their allelic composition, have a tendency to kind of warble around. They shift this way, they shift that way, but they always kind of return kind of the mean time and time again, right? They're very stable. However, when you start to shrink up the population size, that stability quickly starts to disappear. And they can become quite prone to movement in any one direction in terms of their allelic composition, either fixation or elimination. The way to think about this is it has a lot to do with the sampling error that happens with small populations. So an example would be, when you flip a coin, theoretically, what are the odds of getting a heads or a tail? They're 50%. Okay, as long as the coin is balanced properly, it'll be 50%. Now here's the thing, if I flip a coin 1,000,000 times, I should anticipate getting very, very close to 500,000 heads and 500,000 tails. But if I flip it 10 times, and I got 7 heads and 3 tails, would you think the coin was bogus? Most of you don't even think twice about it. Why? Because sampling error comes into play. The smaller the population is, the more prone you are to sampling error, meaning deviations from expected predictions. The bigger it is, if all of a sudden I got 700,000 heads and 300,000 tails, what would I think about the coin? It's screwed up. Something off the coin, okay? But 7 heads and 3 tails, I would think twice about it, right? Sample size is quite different. Well, in a natural population, this is going to apply every time you get a random mating or fertilization that takes place in the population. The smaller the group is in the population, the more likely you are to deviate from expected norms. So, in natural populations, real populations are small in size, but finite. And so, how can this work? Well, here's an example we talked about a little bit. You walk on the lawn, you crush the green bug, there's hardly any green bugs left to generate in the next population for the next, pass on its traits to the next generation because you eliminated them, right? Here's another example using flowers over here. That's really tough to see with that light. Let me see if I can get the light off just a little bit more for this example. Doesn't help at all. All right, I'll just point it out. So, in this example over here, I have 3 generations of flowers, okay? I'm going to look at mine now, I'll show you what I'm looking at. And so there's only 10 individuals here, right? So, in this first case, just by chance events, the top 3 flowers on the left-hand side get to mate, and the bottom 2 flowers on the right-hand side get to mate. So only 5 of the 10 plants are going to leave offspring. Based on the crossing there, I just do the Punnett squares, which we've all done to tedious, right? Infinitum, we don't want to do that anymore, but they're there. So basically, what will generate is generation 2 that looks like that. That's a fairly robust population genetically. Even though the numbers of individuals was small, there's only 10 individuals again, I'm still seeing all the different combinations there. There's homozygous dominant individuals, there's heterozygotes, and there's homozygous recessive individuals. But now by chance event, whatever it might be, only 2 individuals from that population are going to leave offspring. And they happen to be big R, big R, big R, big R, homozygous dominant. What will that leave me in generation 3 now? All exactly the same. They're monomorphic for that particular trait. They're all homozygous dominant. Is that a very diverse population genetically? Not at all. It's all homozygous dominant. I've literally eliminated the small r allele. It is gone by just chance. That's just who happened to mate for whatever reason. All right? That was it. The other ones, I stomped on them. It was too wet. It was too dry. They just couldn't get their offspring off in time. They couldn't pollinate properly, whatever it might be. The bee decided just to go to that flower and not that flower. Chance event. Now, what's the problem for this generation? With this generation right here, in that population, there is no variation at all. Well, it's homozygous dominant right now, but what if all of a sudden the temperature starts to rise globally like it's doing right now? I might be completely out of luck. Or what if all of a sudden my pollinator, for whatever reason it is, has a mutation and decides it doesn't like red anymore? What's going to happen to me? I have no diversity whatsoever. I'm going to go extinct as well. So how's the only way I can get that little R back now? I have to get lucky enough to have a mutation that brings it back into the population. Or, what else? I have somebody who would immigrate in with it, right? Maybe a bee takes the pollen from another population and puts it back. That's it. So that's an example of genetic drift. Chance events quickly did what? I had a diverse population, but it was small in size. And what happened? It quickly diverted to fixation of one particular kind of allele set and eliminated the other. That's a classic example of genetic drift. The smaller the population, the more likely it is to occur and have a big impact on driving allelic frequencies in any given population.